Good day everyone. In this video we're going to be looking at a question from a previous exam paper. So this paper was written in November 2015. It's physical sciences paper 1, and if you look at the question you will recognize immediately that it is a question on electromagnetism. So specifically Faraday's law of electromagnetism. So let us read that question, which is question 10. So in 10.1 they are saying that the arrangement of apparatus to demonstrate Faraday's law of electromagnetic induction is shown below. So before we actually deal with this question, I think it's important for us to identify the different components of this apparatus that is given to us. The first thing that most of us are familiar with, that this is your magnet. It's a bar magnet, and what do we know about bar magnets is that they produce a magnetic field around. Just that in this situation, they didn't actually indicate which part is the North Pole and which one is the South Pole. It doesn't matter. But one thing that you must know about magnets is that around the actual magnet, you actually sort of field lines, because it produces a magnetic field. So I'm not going to show the direction of those field lines, because at this point I actually don't know what is which pole is the north and which one is the south, and I don't think knowing whether this is the north or south is important for this question, right? The second important thing is this thing over here, and this is what we call a galvanometer. So let me just write it down. So that would be galvanometer. And what it does is that you actually, using a galvanometer, you are able to detect current. So current, remember, it's given with the letter I. So it's a very sensitive type of equipment. You just draw a circle with this arrow there, indicating the direction and the magnitude of your current. So it's able to detect very small amounts of current, and another advantage is that you are able to detect, so it's also able to tell us the direction of your current, right? Because remember, another meter that we use to measure current is an ammeter, right? So the difference between an ammeter and a galvanometer is that this one is able to detect very small amounts of current, and it is also able to tell us the direction of that current, whether it's from the positive to the negative or from the negative to the positive. But with an ammeter, you only know the magnitude, not necessarily the direction. So we've spoken about the magnet, we've spoken about the galvanometer. Another thing is the cylindrical thing over there that is shaded in gray, and that we can say it is a core. Normally they use an iron core, Fe, iron core, iron center. So that is your core. It's a conductor as well. And then in addition to that, you have this wire there. See, it's a conducting wire that is able to carry current. And then the difference is that it has now this coil. It's coiled with a number of tens of windings. And the reason why we would do that is to increase the strength of the induced EMF within this entire setup, right? So now the principle of electromagnetic induction, which was which is described using Faraday's law, is that if you now say I'm gonna move my magnet towards this iron core with a solenoid of this number of coils, your galvanometer will actually detect a current. So initially in the galvanometer, you find that the arrow is just pointing at 0 there. right? But as you perhaps move this magnet closer, you'll see a deflection, such as is shown here in your schematic, right? So when it deflects, it means that it is able to detect a current in a certain direction. So maybe it will go there if you move it closer. And then when you now again move the magnet away, you also see a deflection. Maybe during this time your galvanometer will deflect in the opposite direction. Hence, it's able to tell us in which direction is your current flowing. So all the time, if you're moving this thing in and out, this you actually detect a current in your circuit. But why is that interesting? This is interesting because it tells us that we can actually be able to induce current to flow within a conductor by just changing the magnetic field. So when I move the magnet closer, it means the magnetic field is increasing. And now when I start to move it away, it's decreasing. And what is happening is that the magnetic field is changing, and hence current is able to be detected within this entire setup using a galvanometer. If now I keep the magnet stationary, you'll actually not detect any current. So that is essentially the principle of electromagnetic induction, our ability to induce current or even EMF, electromotive force, by just changing the magnetic field. Hope that is clear. So now question 10.1.1 says, state Faraday's law of electromagnetic induction. So this is a 2-mark question. It's something that you should be able to know. You'll find it in any textbook. What do we mean when we talk about Faraday's law of electromagnetic induction? So Faraday's law of electromagnetic induction, so that was question 10.1, says that the magnitude of the induced EMF or electromotive force in a conductor is directly or is equal, is equal to the rate of change of magnetic flux linkage. And the total marks for that question are 2. So the induced EMF in this conductor is equal to the rate of change of magnetic flux linkage. And in EMF simply refers to the voltage that will be detected within this circuit. So if you have current, you also have voltage flowing within that circuit, right? And then the 10.2.2 says, state 2 ways in which the deflection of the galvanometer can be increased. So essentially they're asking you what's a way to increase the current in this system. So there are many ways in which we can essentially do this. So that is 10.2. Is that 10.2? Let me check. It's 10.1.2. 10.1.2. So meaning this was actually 10.1.1, right? Then you have 10.1. I want to do that. It's 10.1.2, right? So there are many ways in which we can increase the strength of the current. So I would say maybe the first one would be to increase the size of the magnet. So a bigger magnet will mean that a higher current or a higher EMF will be induced, because it means that the magnetic field will increase. Another way is that you can increase the speed or how fast you are moving your bar magnet. So the faster your bar magnet is moving, the greater the induced EMF. Increase the speed of the magnet, right? Another way that I would say is that you increase the number of turns of your solenoid. Increase number of turns of solenoid, right? So then the more turns you have, or windings, some books will refer to them as windings, the greater the strength of your induced EMF. And this whole principle is actually what they use in power station. This is how a generator essentially works, because you rotate something, a coil, within a magnetic field, and as you're rotating it, it means that the magnetic field is changing, and as a result you have current in that system. So let us go to 10.2. This is when we begin to do calculations. So they is saying that a coil with an area of 0.6 meters squared is held with its axis coinciding with the direction of a magnetic field of strength 0.4. I think the term there, coinciding, the axis of the coil coincides, that means it's in the same direction as the direction of the magnetic field, which has a strength of that. So I'm going to try to draw that situation. So let's say if you have maybe a north pole here, right, and then you have a south pole, so those are your magnets. This is just a schematic. It means you are aware that the magnetic field lines will always move from the north to the south, right? And then let's say then you have your wire, and your wire maybe it's standing like this, or your coil. Did they say the coil? Yes, a coil. So you have that coil and it's standing like this. The one thing you must know is that the axis, which is the line perpendicular to the coil, in which direction is it in? How to look different? Cream. So the axis of the wire, also the coil, will also be in this direction. Hence they coincide. They are English. They are coinciding. So they are in the same direction. Somebody might say they are parallel. So I'm trying to change the color for this. So if that is the case, then we'll say, okay, if that is the case, I know that my theta, which is the angle between the magnetic field lines and the axis to your coil, is 90 degrees. Or the normal, some books will say the normal, or some book will say the axis, right? No, it's 0 degrees. Remember, if two things are parallel, the angle between them is 0 because they're in the same direction, right? What else do we know? Because now we're just noting down the things that we know. We also know that the area of that is given by, I think they said it's 0.6. We know that area is meter. We need to write it in meters squared. If it's given in centimeters, you must first convert. But here there's no need for a conversion because already it's reported in meters squared. Another thing that they gave us is the strength of the magnetic field. So they said the strength of the magnetic field is 0.4, and that is in Teslas. 0.4 Teslas, just write T. So the magnetic field is something that you need to know is measured in Teslas, right? So now, what is the question requiring us to do? The question says calculate the magnetic flux linkage. So the formula for the magnetic flux linkage is given by this Greek letter phi. So you draw a circle with a line over it, and then you say it is the product of the magnetic field B, the area A, and the cos of the angle between the magnetic field and the axis. So it's the cos of the angle theta. So don't get confused. I think there's normally a lot of confusion in terms of what is that angle theta in this equation. Somebody will think that theta is the angle between the magnetic field lines and your coil. You can clearly see that this coil here is standing perpendicular, but its axis, the line that is normal to it, is in this direction. So this theta is actually the line between the magnetic field lines and the axis to this coil, or the line normal to this coil. When you say something is normal, it means that there's an angle of 90 degrees between it. So between this coil and the normal to the coil, the angle is 90 degrees. Yes. However, the angle between the magnetic field lines and the line that is perpendicular to the coil is 0, because they are all in the same direction. So don't get confused there. So we actually have everything. If you look at it, we have theta, we have area, we also have the magnetic field. So it's just a matter of saying, okay, I'm gonna have 0.4, so 0.4 multiplied by the area, and our area is given as 0.6, right, or 0.6 multiplied by the cos of the angle theta, and we have established that the angle is 0 degrees. So if you remember in mathematics, the cos of 0, how much is that? The cos of 0 is 1. Hence, you just left me with 0.4 multiplied by 0.6. If you don't believe me, you can just input the entire thing in your calculator. Okay, I have 0.4, right? Multiply by 0.6 multiply by the cos of the angle 0. And you actually get a value. The value that I get is 0.24. But remember, the magnetic flux linkage, you must report it in Webers. So 0.24 Webers, you just write WB, and there you are. So that is question 10.2.1. So you'll get a mark for the formula, a mark for the correct substitution, and a mark for reporting your final answer, right? So we move forward, and the question says, wait, where are we? Okay, the question is, we're still at 10.2. Okay, this was 10.2.1. 10.2.1. So the question now continues, and it says to us, in order to produce an EMF of 9 volts, the area of the coil with its axis coinciding with the direction of the magnetic field, so the theta is still 0, they're still parallel to each other, the axis as well as the direction of the magnetic field, is halved. So they will halve the area from 0.6 meters squared to 0.3 meters squared, and they it's halved in 2 minutes, right? And the question says, calculate the number of turns in the coil. So how do we go about it? So you will say, okay, I know an equation that requires me, so that is 10.2.2. Let me start it on the other page. So we say, okay, I know an equation that involves the number of turns, and it's that equation that we described there in ways that the induced EMF, this funny looking Greek letter, it's a Greek letter epsilon, is equals to the negative of the number of turns multiplied by the change in the magnetic flux linkage, that a circle with a line over it, it's Greek letter psi or phi or phi, doesn't matter, divided by the change in time, right? And the question wants you to calculate this. You check, am I given the EMF? Yes, I was given the EMF, and the EMF, they said it's how much? It's 9 volts. What else was given to me? I was given the change in time. So the time it took for them to halve the magnetic, the what I'm lying, the time it took for them to halve the area, right? And how much was that? They said it's 2 minutes. So it's 2 minutes, but the time when we calculate, it must always be in seconds. This doesn't look nice, but you can see. So 2 minutes equals to 120 seconds, because 1 minute is equals to 60 seconds. So it's just going to be 2 multiplied by 60, which is going to give us 120 seconds, right? So I also have this. I have this, and this is what I'm looking for. So this is the missing thing, the number of tens. So I'm seeing that if I have this, I'll also need to find the change in the magnetic field, in the magnetic flux linkage. So you'll say, okay, if I'm saying the change in the magnetic flux linkage, it's going to be the magnetic flux after the area has been halved from 0.6 to 0.3. So I'm just going to say it's going to be the magnetic flux in the beginning, in the final one, right? So if the change is always the final minus the initial, minus the magnetic flux before the area was halved. And if you look in the previous question, we actually calculated that value. So this will actually be the initial magnetic flux. So you have it. But this one, we will say, okay, it's just going to be the B multiplied by the area, which is now 0.3, multiplied by the cosine of the angle theta. Theta, because the two still, the axis and the magnetic field lines, they still coincide, they are still parallel, it is still 0. So cos of the angle theta. And now I know that the initial magnetic flux was 0.24. So I can just say minus 0.24. I don't need to recalculate it because I've already calculated it in the previous question. And then you say, okay, what has changed is that the field, the magnetic field, the sum of the magnetic field still remains the same. The only thing that is different in this scenario now is actually the area, because my area has changed from 0.6 to 0.3. So now I have 0.3 multiplied by the cos of the angle 0. Cos of 0 minus now 0.24. It can fit 0.24. And you don't need to do much now. You just need to put this whole thing in your calculator. So you'll say, okay, let's see what we have. We have 0.4 multiplied by 0.3. I always put my stuff in brackets just to be safe. You know, board mass. Otherwise, sometimes you get wrong answers. Minus now 0.24. You could have just used a multiply there, it doesn't matter. I just like using brackets. Then there you are, the value that you get is 0.12, which is negative. Which makes sense because if you halve or you decrease the area, the magnetic flux linkage will decrease, as this answer is negative, because this value there is lesser than this value. So the negative of 0.12, and it is measured in Weber's WB. So now you're saying, okay, if I look back at my formula for electromagnetic induction, Faraday's law of electromagnetic induction, I now have the change in the magnetic flux linkage. So I need to find L. And before we can do that, we just need to rewrite this whole thing. So you say, okay, how do I make N the subject? You say, okay, if I have E, or the epsilon, the induced EMF, I can just say it's over 1, and then on this side I have the negative of N, which is what I want to calculate, multiply by the change in magnetic flux, all of it divided by the change in T, right? How do I make this N to be the subject? The first step is just a matter of cross multiplying. I'm going to multiply 1 by negative N multiplied by the change in the magnetic flux linkage, right? So if I do that, 1 multiplied by that, it's just going to be the negative of N multiplied by the change in the magnetic flux linkage. And then also, to get the other side of the formula, I'll just say is the EMF, induced EMF, multiplied by the change in time, which is just going to be equals to the EMF multiplied now by the change in time, right? But we're not done. As you can see, I still don't have N, or the number of turns of windings as the subject. To do that, I will simply say, okay, I'm just going to divide both sides by the negative of the change in the magnetic flux, so that at least on this side I'm only left with N. So what you do on the right, you must also do on the left, or what you do on the left, you must also do on the right. It's a maths. And if you look at that, this means that these two values on this side will cancel. So even that negative will cancel that negative there. And if you look at it, you will just be left with N, which is equals to the induced EMF multiplied by the change in time, right? And the whole thing divided by the negative of the change in the magnetic flux linkage, right? Okay, so if we do that, if we have that, then we'll say, okay, what is my induced EMF? They've given you the value, they said it's 9. What is the change in time? They said it's 2 minutes, but you convert it to seconds so that you know it's 120 seconds. And then what is the change in magnetic flux? So you must be careful. You have the negative from the formula, but when we calculated the magnetic flux earlier, it was also a negative of 0.2, 0.12. So a negative multiplied by a negative will be a positive. And if you just put this whole thing on your calculator, you will get a value there. You say, okay. So you say, okay, let's see. I have 9 multiplied by 120, right? Take this to the bottom. Then I have a negative outside. Then inside I have another negative 0.12. Then you get, oh, I need to say equals to, and the value that you get is 9,000. So what does that mean? It means that your solenoid actually has 9,000 turns or 9,000 windings. So you can just write turns or windings, doesn't matter. And there you are. I think this is actually the last question. Yep. And if you had solved this question correctly, you would get your full marks, which was 11 for that question. If something is not clear, please don't hesitate to leave that question in the comments. I'll try to elaborate further. Other than that, I hope this video was helpful.